Last class we looked at two of the processes in the IC fabrication. We first looked at etching, which is a technique for removal of material. We found that we could combine etching with the lithography or patterning to selectively remove material from certain places in the wafer. So etching, we found, could be done either by a wet process, which is your wet etching, or by a dry etching. We also looked at the opposite of the etching process, which is the growth process, where we add material to the wafer. So we mainly focused on growth by a chemical vapor deposition process. Today we are going to continue to look at growth process. We are going to look at formation of metal layers. This process is called your metallization. Along with metallization, we will also look at polishing, where we remove excess material in order to give a smooth finish and remove surface roughness. So today we are going to focus on two techniques. One is metallization, the other is polishing. So before we do that, we said that IC fabrication essentially acts like an assembly line. You start with a blank wafer, the wafer goes through a series of processes and steps, and then gives you the final IC product. So this circuit fabrication is normally divided into two big stages. The first one is called the front end of the line, or FEOL. So this usually refers to the processes that are used to generate the active and the passive components of the circuit. So the transistors, the resistors, the diodes, and so on. So active and passive components of the circuit. The next one is called the back end of the line, or BEOL. So while the front end of the line, all the device components are manufactured, these components have to be connected to each other and also to the outside circuit. So this interconnection is done in the back end. So metallic layers to make the interconnections. To the various circuit components. So later we will see that there is also a contamination reason why processes are divided into front end and the back end. Now metallization process is mostly related to the back end processing. It is defined as the wiring of the different circuit components to get a functioning circuit. Now if you remember, the original IC device that was manufactured by Jack Kilby essentially had external wiring. so the wiring was not part of the IC circuit. But in the first modification that was done, the wiring was made part of the IC circuit and aluminum was the material that was used for doing the wiring. Now, common methods for growing these metal layers onto your IC circuit, they are normally physical vapor deposition techniques. So, the methods for growing metal layers, one technique is called sputtering, and we will see what this means later. So, sputtering is an example of a physical vapor deposition process. Mainly used for aluminum alloys, and it is also used for growing the copper seed layers which are used for electroplating. Another technique is chemical vapor deposition. We already saw CVD last time. We used it for growing layers like silicon dioxide or nitrides or dielectrics, but CVD is also used in metallization. It is usually used, for example, say you want to grow polysilicon for a gate, for materials like tungsten, tantalum, nitrides and so on. And then finally, electroplating. It's mainly used for copper. So, for doing copper metallization, for growing the copper layers, electroplating process is used. The whole idea of copper electroplating and copper metallization is called a dual Damascene process. And again we will see what this process means. So, if you looked at the first generation of IC circuits, usually there was one layer of metals that was added or one layer of metallization that was carried out. So, the first generation devices there was usually a few hundred components per device. So, it is an example of a medium scale integration. MSI. So, you essentially had a single layer of metallization. So, in this process, small holes, these are called contact holes, are first patterned onto the wafer, usually using a mask, and there will be an oxide passivation layer. So, small holes are patterned. Metal lines approximately 0.5 microns thick or 500 nanometers were vapor deposited. So, aluminum was the material that was used for the first generation of IC devices. So, it is possible to vapor deposit aluminum. Usually you can use thermal evaporation or sputtering. After this, the excess metal was removed along with the photoresist. And then finally, the whole system was annealed for allowing to generate good interfaces. So if you want to depict this, say we have a wafer with a certain doped region, so we want to make contacts to this doped region. So in this case you had an oxide layer, just erase this, we had an oxide layer and then a metal layer, so you start off with the wafer which has a doped region. There is a uniform oxide layer that acts as passivation. So the oxide layer is patterned in order to open a small hole. Metal is then deposited, so you have excess metal everywhere. The remaining excess metal is then removed along with the photoresist to leave behind the metal plug, and then usually some sort of annealing is carried out to better develop the metal wafer interface. So in the first layer of IC device, in the first generation of IC devices, metallization was essentially a single layer. So you can think of this as being replicated throughout the entire wafer. Now what happens as we have an increase in component size is that with different higher generations of IC devices, we essentially had greater integration. So you went from medium scale to large scale to very large scale integration and so on. So the individual component sizes reduced, at the same time the number of components increased. So the number of components increased, and at the same time the component sizes reduced. So this meant that because you had more number of components, you needed to make more number of connections. So the number of interconnects increased, but the available area to make these interconnects reduced. Which means we have to make more number of wiring, but the amount of area available is smaller. So one way to do this is to of course reduce the size of the wires. So you make the interconnect smaller and smaller, but even that will not be enough because of the large increase in the number of components. So a typical component now, device now has anywhere around 10 to the 7, so around 10 billion components. So to overcome this, interconnects essentially became layered. So instead of having a single layer of interconnects, it led to the formation of multi-level or multi-layer of interconnects. Again, in the case of multi-level interconnects, you had individual layers of metals that were connected to one another, and they were then isolated by using dielectric materials. Individual metal layers with a dielectric isolation. So let me just draw a brief example of a two-layer interconnection scheme. So I'll just draw this bigger. So now we have the wafer with two doped regions. So this could be an example of a simple transistor. So again we can use an oxide layer for passivation. So now we have the first layer of metals. So the shaded region represents the first metal layer, metal layer 1. So if you think of this as your simple MOSFET, you have a source and a drain, and then you have an oxide layer, and then you have a gate, and you make connections to the source, the drain and the gate. So we can build upon this by having another layer of metal. So we again have a dielectric layer. So this is the dielectric layer. This dielectric layer is usually called the intermetallic dielectric layer. Intermetallic layer, because it separates two metal layers, and then you have another layer of metal on top. This becomes metal layer 2. Again, it is possible to make electrical connections between these metal layers. So in this particular example, I have just shown one MOSFET. If you have a large number of these MOSFETs, again interconnections can be made between these different layers. So as device complexity increased, you can basically end up building more number of these metal layers. So if you look at it, the current 28 nanometer technology has essentially 11 layers of metals, or 11 metallization layers. So we are seeing that with increasing in device complexity, we essentially end up building a large number of these metal layers. There has also been an evolution in the kinds of materials that have been used to make these interconnections. So what are some of the metallization materials that have been used? So the original material that was used for forming the metal layers was aluminum. So in the IC circuit that was developed by Robert Noyce, aluminum was vapor deposited onto the circuit in order to make the metal connections. So some of the advantages of aluminum is that it is easy to vapor deposit. It forms a good bond with the silicon dioxide, because silicon dioxide is used in order to pattern the substrate in open contact holes. Aluminum also has low contact resistance, so by annealing the circuit you could form a good contact with silicon and is also easy to pattern. One of the drawbacks of aluminum though is that aluminum has a low melting point. So aluminum's melting point is typically 660 degrees, but along with silicon, if you look at the aluminum silicon phase diagram, it forms a eutectic, and the eutectic has an even lower melting point. It's around 570 degrees. So aluminum silicon eutectic is around 577 degrees. So pure aluminum, when it was used as a metallization layer, essentially tended to dissolve into the silicon, and this would lead to loss of contact resistance. So aluminum silicon alloys were developed to reduce this dissolution. So typically aluminum with 1.2% silicon was used. Now as the device dimensions reduced and you had more number of components, the dimensions of the individual metallic layers also reduced. So this means the thickness and also the width and the height of these metal layers also became smaller. So this led to a problem of electromigration. So what happens in electromigration is that you have atoms which start to move under the application of an electric field. Also because you had thinner wires, you also had higher resistance, which means there was greater heating, so I square R heating is higher, which again led to movement of material. So this is especially problematic in the case of aluminum, which has a low melting point. So this electromigration again led to cases where the wiring failed, leading to open circuits. In order to prevent this, the next layer of material that was developed was based on an aluminum, silicon and copper alloy. So this was developed to prevent electromigration issues. So a typical alloy composition is aluminum with 1.5% silicon and 4% copper. So in this particular case, the aluminum and the copper formed CuAl2 precipitates, which essentially pinned the grain boundaries and reduced electromigration. Finally now, aluminum is totally dispensed and we have pure copper is used as a metallization layer. So if you look at the development of materials that were used for metallization, we first started with aluminum. Aluminum gave rise to aluminum silicon, and this is to prevent the dissolution of aluminum within the silicon. This in turn went to aluminum, silicon and copper. Copper was added to prevent electromigration of the aluminum, which caused open circuits, and now finally we have copper metallization. This was a process that was started in the 1990s, typically by IBM, but now it is essentially the industry standard, and copper is the material that is used for forming all the metal layers, pure copper. So copper is usually grown by electroplating process, we will see the electroplating process later on, but one of the biggest problems with copper is that copper can diffuse into both silicon and silicon dioxide and essentially form deep level defects. So, one of the issues with copper is that it forms defects in both silicon and silicon dioxide. This can essentially kill the device. What we mean, of course, is that the device loses its functionality, so that copper will essentially kill or poison the device. So, even though we use copper for metallization, usually some sort of a barrier layer is added to separate the copper from the wafer. So, some barrier material is used. Typically materials based on titanium, tungsten, tantalum. So, these could also be nitrides like titanium nitride or tantalum nitride, or even silicides are all used. So, these are essentially used to form the initial electrical contact, and then copper is first vapor deposited and then electroplated on top of it. So, this is another reason why all the IC fabrication processes are divided into front end and back end. So, we saw that the front end processes are essentially copper free, so that no copper is introduced into the device at any of this stage. This is to prevent copper contamination. The back end of the line is where the metallization is carried out. So, here you have copper, and whatever happens in the back end, the wafers never go to any of the front end processes. So, all the front end processes are carried out first before going to the back end where copper is introduced. So, this distinction is maintained very carefully in the fab to prevent contamination with copper. So, for example, if there is any downtime in any of the equipment that is used in the back end, tools that are used for repairing the equipment will not be used for repairing any of the tools that are used in the front end. This is because those tools could be contaminated with copper, and that again can introduce copper contamination in the front end. So, there is a very important distinction between these two types of tools in any operating fab. Similarly, any tools that are used for back end processes will not be used for growing wafers for the front end. So, we have looked at some of the different materials which are used for metallization. So, let us now look at some of the metallization techniques. So, the first technique we are going to look at is sputtering or sputter deposition. So, this is a physical vapor deposition process. It is mainly used for growing both metals and alloys, but generally sputtering can also be used for growing dielectrics, oxides, compounds and so on. So, in this particular case, we just draw a brief schematic. The material that we want to sputter or to want to be deposited is made as the target electrode. So, this essentially consists of atoms. So, I will just show some of these atoms on the electrode. This is taken in an evacuated chamber and then argon ions are bombarded onto the target. So, in this process the argon ions physically remove the atoms from the target material. These are then accelerated onto the wafer and then impinge on the wafer. So, this is essentially a line of sight process, so that the wafer sees the atoms that are knocked out from the target using the argon ions. So, there are different techniques in the case of sputtering. So, sputtering techniques or types. One process is your DC sputtering. You also have something called RF or radio frequency sputtering. Last one is called magnetron sputtering. Sputtering is usually done in a vacuum chamber at low pressure where argon ions are used to sputter. Sometimes you can also have reactive sputtering where a reactive gas is used, so that not only material removal takes place, but the material that is removed reacts with the gas to form compounds. For example, oxygen can be used in order to form oxide layers, boron can be used to form borides, nitrogen to form nitrides, and so on. The next process is CVD, chemical vapor deposition. We have again seen CVD in last class. So, for example, you can use CVD to grow the polysilicon for the gate. This is in the case of a MOSFET. CVD is also used especially for growing the barrier layers that separate the copper from the metal. So, this could be your tungsten, or you could have tungsten reacting with silicon to form tungsten silicide, titanium nitride, or so on. CVD is especially used when you have to fill regions with high aspect ratios. So, for example, if you had a trench, we will see an example of a trench later, and a very thin barrier layer has to be grown in the trench with the correct aspect ratio, CVD process is used. The third process for metallization is electroplating, and it is mainly used for growing the copper layers. So, in the case of electroplating, it is used for copper metallization. So, initially a seed layer of copper is first grown. So, this seed layer is usually grown by sputtering. Usually grown by sputtering. This is typically around 30 to maybe 200 nanometers thick. So, in the case of electroplating, the wafer is taken in a bath. It is a bath of copper sulphate. The wafer forms the anode, the wafer forms the cathode. And there is also an anode, which is your counter electrode. During the electroplating process, the copper 2 plus that is present in solution gets reduced and forms metallic copper. So, the copper in the copper sulphate gets reduced to form metallic copper, and this gets deposited on the anode, which is the wafer, gets deposited on the wafer. This is the cathode. So, once again it is a process where copper deposition takes place. The advantage of electroplating is that it is a low temperature process, can be carried out at room temperature, so that once the barrier is grown, the copper layer can be electroplated directly onto the wafer. The excess copper is usually removed by a process called polishing. So, this polishing process is usually called planarization. It is not only restricted to copper, it is usually used in the IC fabrication to remove excess material and to minimize the surface roughness. So, let us look briefly at the planarization process next. So, planarization is an important process in IC fabrication, especially when we come to patterning, because planarization is used to reduce the surface roughness. And this is especially important when we are trying to pattern multiple layers. This is because we need a flat surface for photolithography, so that we can align the different mass when we have multi-layer lithography. We need a flat wafer for lithography. So, in the case of planarization, another name for this technique is called CMP, which is chemical mechanical polishing. So, in this particular case, the wafer is mounted on a platen. In this particular example, the wafer has some oxide layer. This is the oxide layer. I am exaggerating the thicknesses here. The oxide layer is usually much thinner than the thickness of the wafer. This is just to show the process, maybe with some metal layer on top. So, here I have a wafer with the oxide layer and some metal layer on top. So, this metal layer could have been grown by sputtering or CVD or even by electroplating. But this metal layer is not flat, so if you want to do another patterning and another metal layer on top, we first need to make this flat, and this is done by the polishing technique. So a wafer pad is used. The wafer pad rotates in one direction and the platen rotates in the opposite direction. Another name for this pad is called the polishing pad. Usually some sort of slurry is also fed into the system. So the slurry consists of some abrasive particles that can essentially remove the metal. At the same time, it will also help in giving you a smooth finish. So we have a mixture of polishing pad plus the slurry, and the slurry contains some abrasive particles. So the type of slurry depends upon the layer you want to remove. So the polishing pad is usually made of polyurethane. Slurry for removing oxides, usually SiO2 is used for oxide polishing. Alumina is used for metals. And then you can also use etchants like KOH or NH4OH. So this process is called chemical mechanical polishing because you have mechanical removal of material by the slurry. At the same time, the slurry material is chosen in such a way that it chemically reacts with the layer that needs to be removed and helps in increasing the removal rate. So you have both mechanical polishing and chemical reaction, which is why it's called CMP. So planarization is combined along with copper metallization to create the metallic layers. This process is called dual Damascene process. So let us look at that briefly. So as I mentioned earlier, copper metallization was introduced in the 1990s. It was originally introduced in IBM and then became an industry-wide standard. Copper essentially replaced the aluminum, silicon and copper alloy that was used for metallization earlier. So the copper metallization process is called a dual Damascene process. So this has an interesting historical connotation because the Damascene process was originally introduced in the Middle Ages as a process for generating very good metal inlays, mainly for a decorative purpose. So this process was originally supposed to have evolved in the Middle East, somewhere near Syria, maybe in Damascus, which could be the reason for the name of the Damascene process. So in the case of the dual Damascene process, the first layer of metallization is formed. So this could be a copper separated by some barrier layer. An interlayer dielectric is then grown on top, and then the next metallization layer is formed, and so on. So in the case of copper metallization, this interlayer dielectric, it's called ILD, is usually some sort of oxide. Originally silicon dioxide was used as the dielectric material, but it has a high K, so low K dielectric materials were essentially used. So usually some sort of a fluorine doped oxide is used. Organic based dielectrics can also be used as a dielectric. Example is parylene. So the dielectric layer is usually chemical vapor deposited or can even be spun on directly onto the metal layer. So when we look at patterning using the copper metal layer, we have two terms that we need to keep in mind. One is called a via. A via refers to the layer that connects two metallization layers. And then the other is a trench. The trench refers to the metallization layer which you are trying to pattern. So in the dual Damascene process, both the via and the trench are grown simultaneously. So to start with, the first layer of metallization is grown. So we are going to say that we already have the first metal layer. So a low K dielectric material is then deposited on top of it. So this could be grown by CVD process or by spin on. So then the vias are first etched. So this is called a via first process. So the vias are etched. You can also have a process where you first etch the trench, but here it is a via first process. This in turn leads to a process where you etch the trenches. So you have etched the via, then you etch the trenches, then the second layer of metallization is carried out. So both the via and the trench are filled at the same time. The excess metal is removed by chemical mechanical polishing to give the final two layer metallization. So this is layer 1, that is layer 2, that is the low K dielectric. So this process can be repeated to build the subsequent layers. So this is an example of a dual Damascene process where the vias are first etched. You could have a similar process where the trench is first etched and then the vias are etched. So far we have looked at all the various steps that are involved in the fabrication of your IC device. You start with a blank wafer, then you go through these series of steps to give you the final product. The next class we are going to look at how we actually evaluate the process. So what are the various ways we can measure the process at various stages in order to make sure that everything is proceeding correctly.